Okay, so we're back and we're going to go on to section 2.2, which is called complex numbers. And we're going to start with the concept of a radical. So, we keep touching on things throughout the semester. In fact, we were just talking about square roots and so on, which kind of talks about radicals as well. But let's talk about a radical. So the number that goes inside the radical is called the radicand. And then whatever root we take, whether it's a square root or a third root or any root for that matter. So if it's a 2, we simply say it's a square root and we don't even bother putting the 2 there, but you could put it there. But whatever number you do put there is called the index. So in this case, let's put the 3 there for that. And the answer to this, the third root of 8, is of course equal to 2, as we stated before. Okay, so that's kind of what a radical is and all the different parts of it. But throughout the semester, we keep coming up against various radicals. So for example, the square root, if we get the square root of 25, certainly we know what to do with that, because the square root of 25 is equal to 5. Okay, and then all the other perfect squares go the same way. So that's pretty straightforward. But when you get the square root of 8, we don't quite know what to do with that. You could put it in your calculator and figure out that the square root of 8 is some weird decimal that goes on and on and on and on. Or you could do something called simplifying the radical expression. And what you do is actually separate the square root into 2 parts, so that one part is the perfect square and the other part is the radical. And actually, I think I'd like to switch that around and make it the perfect square here and the radical over there. Okay, so the square root of 8, the perfect square factor of 8 is 4, and you're left over with that. The square root of 4 is 2, and the answer is 2 times the square root of 2. This is called simplifying a radical. And this is something that you're going to be expected to do when you do more difficult problems next week and the week after, and so on. The square root of, let's say, 27. So what you do is, to simplify this radical, you ask yourself, what is the largest perfect square? What is the largest perfect square factor of the number? What is the largest perfect square that divides into 27? And so you have to know your perfect squares. Now this would be 9. And then whatever is left over, which is the 3. So the perfect square factor of 27 is 9 times 3 is 27. Now you could take the square root of 9 and get 3, and then you just bring along the radical. Again, that's called simplifying a radical expression. Okay, so I'd like the class to simplify this radical. Everybody do that now, based on what I've just done. Okay, that's all the time you need, because you should know the perfect squares, and therefore you should know that the largest perfect square, well, first of all, some people may say, well, let's see now. How about the square root of 4 times the square root of 12? 4 is certainly a perfect square, so there's the answer. But that's not good enough because you did not choose the largest perfect square factor of the number. The largest perfect square factor of 48 is 16. Now, this can only be known if you know all of the perfect squares. But the largest perfect square factor of 48 would be 16. And that's what you have to put there, 16. And then the square root of 16 is 4. And bring along the square root of 3. And that's how you simplify the radical. And you have to do that. You can't just, we were leaving radicals the way they were when we were doing other types of problems, but you can't do that anymore. You now have to actually simplify the radical.
Sorry.
Now, the question comes in, okay, this is all very nice, but what happens when you get the square root of, let's say, -8? Uh-huh. Can we take the square root? Is there can we take the square root of -8? The answer is no. There's no number times itself that will give you a -8. So what we do is we divide this into, okay, well, this -8 can be written as -1 times the square root of 8. So you see what we've done is we've separated the square root of -8 into the -1, and now we have a +8. So now we could say, okay, great. Just as we did earlier over here, we can now simplify the square root of 8 into the square root of 4 times the square root of 2 times the square root of -1. Okay, so this became this, and then we took the square root of 8, and that became the square root of 2 times the square root of 4. Now, what can we do here? Well, the square root of 4 is 2. And there's not much you could do with the square root of 2, but how do you deal with this? What do we do here? Well, mathematicians over the years have come to the conclusion that let's take the square root of -1 and call it by the letter I. And they decided that this would be known as an imaginary number. Mathematicians have a way with words. They take very difficult concepts and find a nice, simple word to describe it. So they're saying, well, we don't know what to do with it. It's imaginary. So let's call anything that winds up with this as an imaginary number. And they said that I shall be equal to the square root of -1. Well, that's great for us because now we can come back to this problem and say the square root of -1 is I. This is what we have, and now all we have to do is make this look very nice by moving the I over there, and this would be the answer to the question. Now, one of the things that's very, very useful to us is not only I, but I squared. I squared, How do we do this? Well, I squared is equal to I times I. But what is I equal to? I is equal to the square root of -1. The square root of any number times the square root of any number is equal to the number inside, and therefore I squared is equal to -1. Just remember these two things. This and this. These are the only two things that you're going to come against throughout the semester. Okay? That I is equal to the square root of -1 and I squared is equal to 1. Incidentally, just thinking about this, how about I to the 4th? Does anybody want to hazard a guess as to what I to the 4th is equal to?
I think it's equal to 1,
How'd you get that?
because if you do, I don't know how to explain it. I forgot how, I know this, is just I forgot.
You know it's 1, but you don't remember why it's 1.
Yeah.
Right? Okay, well, that's fair enough. That's okay. Now, this is equal to, this is how I would explain it. But I'm the teacher, so okay, there it is. We know that I to the 4th is equal to I squared times I squared, right? Because 2 plus 2 is equal to 4. We know that I squared is equal to -1. I squared is equal to -1. And what is -1 times -1? +1. So I to the 4th is equal to +1. These are the three things you really should know. There are other things like I to the 38th power and all that stuff. And there's actually a problem in the homework, which you can forget about. That's not, I don't want to go into that. After years of teaching this course, I'm trying to narrow it down to just the very basic things that you need to know. This is very, very important. This is important, and this could be important. Okay, so these are the three things I'd like you to know. So let's go on and simplify a radical expression that has a negative number in it. So, for example, well, here we go. The square root of -25. Okay, so we want to separate this into two parts. Take out the negative and put it there. And then here you have the square root of 25. The square root of 25, we all know, is 5. And the square root of -1, as we did up here, is equal to I. That's the answer to the question. The square root of -48. Okay, well, we separate, well, it's not a perfect square. If you take out the square root of -1, it's still going to be the square root of 48, which is not a perfect square. So there are three parts to this. The first part is the -1, and that goes over there. Now we have the square root of 48 left, and now we go back to what we were doing up here, not too far up, right? Can you still see? Yep, you can. The square root of 48 is the square root of 16 times the square root of 3. So we separate this into a perfect square, not a perfect square, and an imaginary part, the square root of -1. This is called a rational number. This part right here. Let me kind of put that over there like that. This is called an irrational number. And this is the imaginary part. So whenever you take the square root of a negative number, always separate it into 3 parts: a rational number, an irrational number, and rational means simply that you could change this to a whole number. Irrational means you cannot do such a thing. And the imaginary part goes over there, which is I. And in general, mathematicians have come to kind of separate this. This is now the way it's all separated, but it looks nicer like this. This would be the acceptable answer right there. A rational part, an imaginary part, and an irrational part. Okay? In the same way I just did this one, simplify the square root of -72. Everybody take a few minutes and do that now. Well, what strikes me about this problem is the very first thing you want to do is this. You want to do that first. And now 72. What's the largest perfect square that divides into 72?
$36.
Good. Good. Who said it?
Talia.
Good. I was afraid somebody was going to say what number. Well, we'll talk about that in a minute. Let's follow through what Talia said. So 36 and 2. Okay, so the square root of -72 will be the square root of 36, there's the rational part, the square root of 2, there's the irrational part, and the square root of -1, and there's the imaginary part. Okay, so this becomes equal to 6. This becomes equal to the square root of 2. Can't do anything with that. And the square root of -1 is I. Now let's move that I where it belongs. And that is the answer to the question. And when I was talking about what I was afraid somebody was going to do, I was afraid that somebody would say, all right, how about 9 times 8? Is that okay? Did anybody do that? It's easier to see that the square root, that 9 is a factor of 72 than it is 36 is a factor of 72. So you could do this, right? But then you have to deal with the square root of 8. Right? So what are you going to do with that? You're going to have to do that also. And this becomes 3 times 2, which equals 6 times the square root of 2 times I. And this is exactly the same thing as, the answer is, but you had to go through an extra step. So you could do a smaller perfect square, but then you just have to do an extra step, but you always wind up with the same answer down here. And that is how you simplify a radical expression that has an imaginary number contained within it. Okay, now I'd like everybody to take a look at this problem and see what you could do with it. Well, what you should be doing is saying, well, there's not much I could do with this 5. Let's just leave it. That's about as simple as it could get. But the square root of 80, negative 80, put the -1 there. The largest perfect square factor of 80 is 16. I mean, you have to know your perfect squares to do this. You know, you have to know, 1, 4, 9, 16, 25, 36, 49. You got to know them. You got to know them. And then this will be 16 times 5. Now, this can be simplified to a 4. You have to leave that, and that, you put the square, you put the I, and this would be the answer to the question. Anybody not see this? I did nothing with the 5. All I did was really the same type of problem we've been doing, which is to take the square root of a negative number and separate it into a rational, an irrational, and an imaginary number. Now, whenever you have a binomial which has a real part, this is a real number, and an imaginary part, this is called a complex number. And the general form of a complex number will be A plus BI. And in this particular case, this is the real part, and this is the imaginary part. This is called a complex number. And we're going to talk the rest of the class about adding complex numbers, subtracting complex numbers, multiplying complex numbers, and dividing complex numbers. So first, let's talk about adding complex numbers. And here's a typical problem. Now, what you would basically do here is take this problem and either just go like this, drop the parentheses at this point. So one way of doing this is to just do 3 minus 7i plus -4 plus 2i. And you don't even need this double sign here. You could simply make this into -4 and just combine like terms. +3, -4 is -1, and -7i, +2i is -5i. And this would be the answer. This is how you add complex numbers. The other way of doing this, if you wanted to kind of simplify it in your mind a little bit, what you could have done was gone 3 minus 7i and -4 plus 2i, make it into an actual addition problem with the like terms, so to speak, one underneath the other, and you wind up with the same answer. It doesn't matter. You could either do it this way or you could do it this way. And that's how you add complex numbers. It's no big deal. So I don't really want to spend an awful lot of time on this. but that's how you add complex numbers. Let's talk about subtracting complex numbers. And I'll leave this problem to you to try on your own. What I would do in this problem is I would leave it the way it is. All over there, leave that the way it is. But now, just do the distributive property here. Do -1 times 12 minus I. And this would give us 5I plus 3. Now, -12 and positive I. Okay, I'm just using the distributive property to make it easier for myself. I stuck in a 1 because there was no 1 there, so I put in a 1. And then I just multiplied. This times this times this. And now let's just combine like terms. 5I plus 1I is equal to 6I. And positive 3 and -12 is -9. Now, if you want to put it in A plus BI form, you can even change this to -9 plus 6I. I like this answer better because it's more in the form all the way up here to the top of A plus BI. See, so I like to keep it like that because you never know what's coming up next. That's called subtraction of complex numbers. Okay, so it's like adding 5x plus 3y. You just combine like terms. Let's look at multiplication. Multiplication of complex numbers. And let's take the problem I have up here, 3 plus 5I times 1 minus 2I. Again, I will leave this to you. Okay, let's go through it. So I'm just going to do this the way I would normally multiply a pair of binomials. So 3 times 1 is 3. 3 times -2I is -6I. 5I times 1 is positive 5I. I'm doing it, right under, because I see that they're like terms, so I might as well put them together. And then positive 5I times now watch out here. First of all, the positive times the negative is negative. 5 times 2 is 10. And don't forget, I times I is I to the second. Now let's simplify this and see what we get. So this is a 3. This becomes I. And this becomes 10. Now remember what we said earlier. I squared is equal to -1. See how important that is? You have to know that I equals the square root of -1, but I squared is equal to -1. These are very important. And then the third one we did, I to the 4th is equal to +1. These are the 3 that you need to know. All right, so here we are. Now, what do we do here? Well, the -10 times the -1 is +10. A negative times a negative is positive, and 10 times 1 is 10. Now, we have a 3 and a 10. We can combine them and get 13 minus I. And this is the answer to the question. Oh, yeah, that's it. Are there any questions? So as you saw, we did adding complex numbers, subtracting complex numbers, multiplying complex numbers. And as you might expect, the next thing we're going to do is division of complex numbers. Now, the first thing we need to talk about is a concept called rationalizing a denominator. Rationalizing a denominator. Mathematicians do not like to have anything in the denominator of a fraction other than a real number, a real rational number. So if you get something like 3 divided by the square root of 2, mathematicians get very upset about that. Hey, you just can't deal with this because, well, yeah, what's the square root of 2? 1.414, it goes on and on. So let's get rid of the radical in the denominator. So they do something called rationalizing a denominator. And what they do is multiply the numerator and denominator by what the denominator was. So the denominator is the square root of 2, but if you multiply the square root of 2 by the square root of 2, you wind up with just a 2. Ah, perfect. If you want to get rid of a square root in the denominator, just multiply by the same radical. And as we've said many times, the square root of a number times the square root of that same number is equal to the number. But don't forget that we now have to put this. And this would be the answer. This is called rationalizing a denominator. The same is true with imaginary numbers. If you have like 5 divided by I, again, mathematicians do not want to have to deal with an imaginary number in the denominator any more than they want to have to deal with an irrational number in the denominator. So once again, they multiply by I divided by I. We know that I times I is I squared, and I squared, well, let's just write it. And here it's just going to be 5 times I. But we know that this, here it is again, this I squared is equal to -1, and this becomes equal simply to -5i. Okay, so it's called, this is called rationalizing the denominator, but there's no real word for unimagining. There's no way of putting it, so they simply call it division of imaginary numbers. Okay, just keep that in mind for a moment. Let's look at this. Hang in there a little longer, folks. We've done a lot today. I understand that, but just hang in there a little longer. Now, what do? How do we get rid of that? See, this was easy to get rid of the irrational number. You simply multiplied by the same irrational number. What do you do here to get rid of that square root of 5? Well, what we do is we multiply by something called the conjugate. The conjugate is 2 plus the square root of 5. Now, what happens? Why is that so special? Because if you multiply 2 plus the square root of 5 times 2 minus the square root of 5, look what happens. This becomes 4. This becomes -2 times the square root of 5. Okay, I'm just, multiplying a binomial, positive 2 times the square root of 5, and negative 5. Square root of 5 times the square root of 5, as you know by now, is equal to negative 5. Now, what happens? Very interesting. Look carefully. We bring down the 4. We bring down the 5. But what happens right over here? This drops out completely. And that's exactly what we want to happen. And we wind up with 4 minus 5, or negative 1 in the denominator. And these numbers are called conjugates because it's the same numbers, 2 and 2, square root of 5, square root of 5, but one's positive and one's negative. And when you have that situation, the middle term drops out. And that's exactly what we want to happen. The only trouble is, once again, you have to multiply by the numerator, but nobody cares if the numerator has a radical in it, as long as the denominator does not. And this becomes minus 3 times 2 plus the square root of 5. And that's it. You don't even need the 1 in the denominator, really, right? By now in pre-calculus, the answer would simply be negative 3 times 2 plus the square root of 5. That's called rationalizing a denominator. And 2 plus the square root of 5 and 2 minus the square root of 5 are called conjugate binomials, or just simply conjugates. We have time, running out of time, so I'm going to move ahead to the very last thing. The very last thing is, what do we do with something like this? Extra credit for the person who could tell me what we want to do here and how we do it. Double extra credit if you're still awake and you could tell us what to do.
Do you multiply by positive 2i?
Well, tell us the whole thing. Not just positive 2i, but what?
It's the conjugate of the negative 2i?
It is indeed. So what is the conjugate of 5 minus 2i?
5 plus 2i.
There it is. Very good. You get it. You get the extra credit. And therefore, don't forget to also multiply the numerator by the same thing. And because these are not just conjugates, but because we're talking about complex numbers, these are called complex conjugates. These are called, because they're complex numbers and they're also conjugates, we call them complex conjugates. Now let's see what we get. In the numerator, it's just going to be 3 times 5 plus 2i. In the denominator, let's do it now. So let's go over here and do 5 minus 2i and 5 plus 2i. Okay, so let's do 5 times 5 is 25. 5 times 2i is 10i. Negative 2i times 5 is negative 10i. And negative 2i times positive 2i is negative 4i squared. Okay, so reviewing, I'm just multiplying a pair of binomials, basically. 5 times 5, 25, 5 times positive 2i, positive 10i, negative 2i times 5, negative 10i. This is the important thing, right? And then negative 4i squared. And this is what we get. We get 25. This drops out as it is supposed to. And this becomes minus 4 times negative 1, which is 25 plus 4, which is 29. So that 29 that we just found from over here goes over here in the denominator of the fraction. So I'd like you to simplify the following. Let's see. Well, let's make it, if it's on the test, I guess we'll make it hard, right? Sorry about that. And let's make this part at least a little easier. Okay, work on that one. That will be the last problem of today. Okay, we need to move a little bit because we're running out of time. I know this is a kind of a complicated problem because not only do you have to deal with this, but you also have to multiply a pair of complex conjugates up there. So it's kind of challenging problem. 1 minus 5i times 1 plus 5i. Let's do that first. So 1 times 1 is 1. 1 times 5i is 5i, negative 5i, and negative 25i squared. This is 1. This drops out, which is exactly what's supposed to happen. And then 25 times negative 1 is equal to, when we change the signs, 26. So the denominator is 26. The numerator is a different story. Okay, so that's going to require a little work. 3 plus 4i. We did this earlier when we were doing multiplying complex, multiplication of complex numbers. So 3 times 3 times 1 is 3. 3 times 5i is 15i. Plus 4i, I'm lining up the like terms, and then positive 20 times I squared. Okay, so once again, I'm just multiplying two binomials, basically. This is 3. This is not supposed to cancel out, remember, because we just simply multiplied two complex binomial expressions, plus 20 times negative 1. Don't forget the I squared becomes negative 1. Now let's simplify this further. 3 plus 19i minus 20. And this 3 minus 20 is negative 17. And so we got rid of that, plus 19i. That's it. That's it. So there it is. And we put that up here in the original expression. And there's the problem right there. There's the answer to the problem. Does anybody have anything different? Because I kind of was rushing to get that out of the way. And I hope I didn't make a mistake. It looks pretty good. Anybody else get that answer?
I did.
I did.
Good. Good. Well,
Is it fine if we write the answer as 19i minus 17.
Nobody is gonna, I would never, okay, so the question is, can you write it as 19i minus 17 over 26? The answer is you should do it this way, but if this was done on a test, I wouldn't mark it wrong. It's still a right answer, it's just not in the A plus BI form, which you gotta, try to get that, try to learn how to do that, because that's helpful in future mathematics, higher mathematics. But if anybody did that on a test, that wouldn't bother me. That's fine.